Hello and welcome to Mathematica's brief introductory presentation on balancing chemical equations. Balancing chemical equations is really one of those topics that a lot of people initially have trouble with, but as we get more comfortable with the subject and then we do more and more examples, I think that they'll begin to feel a bit more comfortable with it. So I've written out basically three rules that we always have to abide by whenever we're trying to balance a chemical equation up here. Number one, equal numbers of the same type of atom must be represented on each side of the balanced equation. And really, where this comes from is this is a direct representation of the law of conservation of mass. And what the law of conservation of mass states is that matter is neither created nor destroyed. So whenever a chemical reaction takes place, we always have to have the same numbers of each element really on both sides of the equation. So that's pretty straightforward. The second contingency is that only coefficients can be altered. We can't actually change whatever the subscripts are within each compound. And really, if you think about it, the reason why that is that we could always take different quantities of one compound or another and change them within a given reaction. But however, it's impossible to alter the number of atoms that are being bonded chemically with one another within each respective compound. So that's where that comes from. And finally, number three, the formula must express whole number coefficients. We can't have any decimal coefficients whenever we're writing out chemical formulas. So essentially, whenever we're looking at some sort of balancing chemical equation problem, like the one I'm just going to write up on the board here, we're always going to be given what's called a skeleton equation, or really an equation that hasn't been balanced, and it's up to us to try to find the right coefficients to balance it. So the one that I'd initially like to take a look at is KClO3 yields KCl plus O2. So initially what I like to do is I really like to take it piecemeal and take apart each individual type of atom or each element within the compound and then see how the quantities match up on either side of the equation. And I think that as we do more examples, what I'm saying is going to gradually make sense. So, as I said, I like to take each element once at a time. So initially, if we look at this, we see that we have potassium, chlorine, and oxygen. Those are the three types of elements on each side of the equation. So now that we're essentially working with three types of elements. So, right off the bat, we know that if we take a look at this, I see that I have one potassium atom on the left-hand side of the equation, and I also have one on the right-hand side of the equation. So that's good. We have the same on both sides, and now we could start to move on. Chlorine. Now I have one chlorine atom here in this compound on the left side of the equation, and on the right side of the equation, I have a chlorine atom here. So that's good. Nothing wrong there. Now, however, I have two oxygens on this side of the equation and three oxygens on this side of the equation. And I'm just going to work right now on this side of the equation because oxygen is completely alone over here. It's not actually in a compound with anything else. So if I start to use coefficients to take various quantities of O2, I'm not going to be altering the numbers of potassium and chlorine as they would if I did it on the left-hand side. So I know that to get 2 equal to 3 using coefficients, I have to multiply by 1.5, because 1.5 times this entire thing will give me 3 atoms of oxygen. So if I rewrite the equation using that coefficient, I keep the left-hand side the same, I get KClO3 yields KCl plus, and I'll do this in red so you know what I'm talking about, 1.5 O2. So now what I like to do is check to make sure that I haven't made any error at all. On the left-hand side, I have one potassium, one chlorine, and three oxygens. Now on the left-hand side, I have one potassium, one chlorine, and 1.5 times 2 oxygens makes 3 oxygens. Now you might be tempted to say we're good and now we could just move on. However, that's not technically the case. If you look up here at the rules that I outlined, you'll see that, sorry, not number 2. Number 3, the formula must express whole number coefficients, so we can't have this 1.5. So the way to knock out that 1.5 is to multiply both sides of the equation by 2. So now I get 2, let me do this in blue, 2 molecules of KClO3 yields, and then I apply this 2 to each of the compounds on this side of the equation. So now I get 2 KCl plus 3, because 1.5 times 2 makes 3, 302. And now, if you want to check to just make sure that we haven't made any sort of error, we know that now we have 2 potassiums, 2 Ks over here. We also have 2 Ks over here. Now we have 2 chlorines, 2 chlorines. Now we have 2 times 3 oxygens. That's 6 oxygens over here. Now we have 3 times 2 oxygens on the right-hand side, and we have, in total, 6 oxygens on this side of the equation. So that's good. The equation is now balanced, and we could box in our final result. If we want to do another example, we could take a look at, what's a good one to do? We could do NaCl plus F2 yields NaF plus Cl2. Again, just as we did up here, we're going to take apart each individual element separately and then see how the quantities match up on either side of the equation. So what I think I'm going to do is I think I'm going to take a look at sodium first. I know that I have 1 sodium on the left-hand side, and I also have 1 sodium on the right-hand side. So that's all good. Nothing's being changed there. Now I know that I have 1 chlorine on the left-hand side, and then I have 2 chlorines on the right-hand side. Now this is an issue, because remember, I always need to have equal quantities of the same type of element or the same type of atom on both sides of the equation. So now, one way that I like to do it is I always like to work with compounds that only have one type of atom in it, which is called a monoatomic compound. So if I look at Cl2, if I want to ask myself, how can I get 2 to somehow reduce to 1 using a coefficient, I know that I could multiply it by 0.5. So now if I were to rewrite the equation, it would be NaCl plus F2 yields NaF plus, and I'll do this in red, 0.5 C, oops, do that in blue, 0.5 Cl2. Alright, so now my chlorines are for the most part balanced. So now really the only thing that I have to take a look at now is my fluorine ions, because really I've already balanced sodium and I've already balanced chlorine. Now, looking at the left-hand side of the equation, I know that I have 2 fluoride ions, right, in a compound. And on the right-hand side of the equation, I have 1 fluorine. So like I said, I always want to try to work with monoatomic compounds, because I find that if you do that, then you don't have to change the numbers of other types of atoms that would otherwise be in that compound, and you have less error margin that way. So now, if I want to somehow ask myself how I could get F2 to reduce to F, just like it is on this side of the equation, I can multiply this by 0.5, because 0.5 times 2 would be equal to 1. So now, if I would rewrite the equation using the coefficient I just found, it would be NaCl plus 0.5 times F2 yields NaF plus 0.5, just carry this over, 0.5 Cl2. The only problem is that, as we just talked about up here for number 3, the formula must express whole number coefficients. So one way to knock out these 0.5s is to multiply both sides of the equation by 2. If I were to do that, put coefficient of 2 here, and I multiply both sides by 2. Remember, I have to distribute this 2 to each one of the separate compounds. So now I would get 2 NaCl. I'm trying to do this in different colors so you know what the coefficients are. 2 times 0.5 F2, that's just going to be 1 F2, and because the 1 is implied, we don't really have to write it. Now again, we have to distribute this 2 over to NaF, so now we have 2 NaF, and again, distributing this over with 2 times 0.5 is 1 Cl2. Again, because the 1 is implied, we don't necessarily have to write it. So now this just becomes 2 NaCl plus F2 yields 2 NaF plus Cl2. I should probably write that in blue to keep with the system. And now if we want to just do a double check one more time to make sure that we haven't made any errors, we know that we have 2 sodiums over here, 2 sodiums over here, 2 chlorines over here, 2 chlorines over here, and 2 fluorines over here, and 2 fluorines over here. So now we know that the equation is balanced, and we could box in our final result. Anyway, I hope that this gave you a pretty good understanding of what we're talking about whenever we say balancing chemical equations, and hopefully this will help you as you go along in the future with some of your different problems that you might face in the future. And good luck, as always.